this module, we will be talking about valence bond theory of diatomic molecule. In the previous module, we have seen how do we apply Schrodinger wave equation to simple systems and get the eigenvalue and the eigenfunctions. I also talked about the some approach to approximation methods also we did. Okay. Now what today we are going to do is you are very familiar with these things. You have been taught from the very beginning that whenever atoms combine to form molecules, they share their electron pair and then they form the bond. That was the original octet rule given by G. N. Lewis. So all of you are aware of the electron dot structure, and you say that the sharing of electron gives a covalent bond formation. Now, even though the two atoms which is combining has a positively charged nucleus, but what we say that when they combine together, electrons share together and they form bond even after the repulsion of in the presence of the nuclear repulsion. So this you are aware of, and this you have been taught from the very beginning. Now we are going to investigate this covalent bonding between two atoms, taking H2 molecule as an example. That in quantum mechanics, how do we treat this covalent linkage between two hydrogen atoms? Okay. The moment I say we are going to talk about what happens that when you are doing with the valence bond theory, then valence bond theory is actually an extension of the electron dot structure, okay, given by Lewis. Okay, and we say that the concept of sharing of electron pair in terms of quantum mechanics became overlap of atomic orbitals. So earlier you used to say that sharing of electron takes place. Now once we have done quantum mechanics and you have seen that what is the electron, it's actually the orbitals where the probability of finding electron is maximum, and that orbital picture you have seen, we have plotted the S functions, S square functions, S functions and P functions, and you have seen the spherical and dumbbell structure. So electron is not something which could be shared. Actually electron is a electron cloud. So we say in terms of quantum mechanics, this sharing of electron pair became the overlap of atomic orbitals. But with this model of binding between that molecule, what is the limitation is that we always talk about two centered and two electron bonds. So you must have two electrons and you must have two centers, then only the overlap of atomic orbital will take place. With this limitation, you cannot treat H2 plus molecule ion in valence bond theory. H2 plus molecule ion cannot be treated in valence bond theory. Valence bond theory, VBT, does not support the formation of H2 plus molecule ion because it always talks about electron sharing, and so there must be two electrons or there must be two orbitals which is overlapping. Okay, that is so H2 plus molecule is not in the valence bond theory regime. And then we say that the concept of resonance to the molecule, if we add, then also adding on to the VBT the concept of resonance to the molecule with more than one center. Okay, so what does it mean? It means that the concept of resonance is, all of you have done in organic chemistry resonance, and what you say, the simplest example in your school days you were taught about is the benzene molecule, and which you say that there could be a change in the bonding and you can have two different structures, many more, but this resonance you are all of you have done it. Okay, so here what happens that the two electrons does not remains fixed to the two centers, the center keeps on changing. Okay, and even if we add this, the one of the strongest limitation of the valence bond theory is that any excited state can't be assessed here. Okay, so even after this excited state can't be described in valence bond theory. So this is the limitation of valence bond theory. In contrast to this, if you talk about molecular orbital theory, here we say that electron move in potential of multi-nuclei of the molecule. You have a field of the different nuclei. It could be 2, it could be 3, it could be 4, and electron also could be anything 1, 2, 3. So it is a multi-centered, multi-electron, or one electron multi-centered. Any concept is applicable. So it's in the sense more general theory, molecular orbital theory, as compared to valence bond theory. Okay, and when we say either in valence bond theory or in molecular orbital theory, you have to write the Hamiltonian for the system. Hamiltonian you will be writing, and if you look at the case of H2 plus molecule ion, then H2 plus molecule ion is the only system which is exactly solvable in the molecular system. Rest others are not, but H2 plus molecules are exactly solvable, of course, with the variation treatment that is there. Okay, with that we can solve. Then in molecular orbital theory, we say that atomic orbitals linearly combine together to give you a wave functions for molecular orbital. And for this combination, you require that the combining atomic orbitals must have similar symmetry, must have similar energy, and must be capable of overlapping. Then only these orbitals will combine through LCAO. Linear combination of atomic orbital is in short called LCAO. Okay, and this gives you the wave functions from which you proceed for finding out the energy and the eigenfunctions for the system. Okay. Then the advantage of molecular orbital theory is that you don't have to do anything special, okay, for explaining the excited states. So the explanation for the excited state comes on its own when you treat the molecule by molecular orbital theory. It's a more general theory, but the disadvantage is that it is too general and it overestimates the ionic structure. Okay, so we will see what does it mean. It is too general and it overestimates the ionic structure in the due course of treatment of H2 plus molecule. I will talk about. Okay, so this is basically we are talking about diatomic molecules. We will take up polyatomic molecules when we are finished with the diatomic molecules. And if you have to treat these molecules, then what you have to do is you have to write the Hamiltonian. So Hamiltonian of hydrogen atom you are aware of. What you can write is that if this is your hydrogen atom with a hydrogen atom, then what you write? You write the Hamiltonian. The first part is kinetic energy term for the nucleus. This is a nucleus term. So A I have given you, and then you have, this is the electron. This is for the electron. Mass also I have written the same. I could have written Mn and Me. So just to differentiate that this one is the nucleus, another is the electron. So you have two centers, one E plus charge on the nucleus and E minus charge on the electron. So there will be an attraction between the two plus and minus charges, and the distance of separation is r. So the potential energy will be 1 by 4 pi epsilon naught E square by r. This I can write. So this term is, this together is what potential energy, and this together is kinetic energy term. So you have the kinetic energy term written. Okay, and total Hamiltonian will be this one for a hydrogen atom that we have done earlier also, since we have done the explanation for hydrogen atom. So it's just a repetition of what we did earlier. If we have H2 plus molecule ion, then what can we write? In H2 plus molecule ion, I have shown it by two atoms A and B. So A nucleus and B nucleus, and we have an electron. So electron is attracted by the A nucleus. The distance of separation is R1. Electron is attracted by B nucleus. The distance of separation is R2. And in addition to these two attraction, there is the internuclear repulsion also, and the distance of separation between the two nucleus is capital R. So what will you write? You will have to write, whenever you write the Hamiltonian, you will have to write the kinetic energy term and potential energy term. And for kinetic energy term, you will write the minus h cross square divided by 2 mass of the particle multiplied by the del square. So this del square will be for all the particles, for both the nucleus and the electron. So this is for the first nucleus, A nucleus. This is for the second nucleus, B nucleus. This is for the electron, this one. So if I have written mass everywhere m, then please correct it, because this will be the mass of nucleus A, this will be the mass of nucleus B, and this will be the mass of electron E. Okay. So this subscript I forgot to give, and you can give it. Okay. So this differentiates that the initial two terms are the terms for the kinetic energy for nucleus in case of H2 plus molecule ion. And then the first term is attraction, because the negative sign is here. Whenever you have a negative sign, it is attractive term. So 1 by 4 pi epsilon naught E square by R1, supposing that the nucleus also have the same charge E, which will be obviously will be because you have one electron and one proton, and the charge is unit charges, you know, in the atomic unit this charge is 1. Okay, so this is E square by R1 minus again minus sign, so this is also attraction. So attraction between this electron and B nucleus. So it will be also be 1 by 4 pi epsilon naught E square by R2, because the distance between the electron and the B nucleus is R2. Then there is the internuclear repulsion R. So this repulsion is given a positive sign, and you have 1 by 4 pi epsilon naught E square divided by R. So this is the Hamiltonian for hydrogen atom. So by now you should have this knowledge that how to write the Hamiltonian for a given system. Okay, that's very must. That's a must for all of you. That this is very simple. Just you have to concentrate on the particle present and on the kind of interaction, possible interactions in the system. Okay, and then you will be able to write the Hamiltonian. So for H2 molecule, what happens? Now in H2 molecules, you have 2 electrons and 2 nucleus. So again, so for 2 atoms, I have given the symbol A and B. Okay, and again you can write the mass of A, mass of B, mass of electron. Mass of B. Then you have electron 1, so mass of electron 1 you can write, electron 1, this will be mass of electron 2, okay. So we have 4 particles, 2 nucleus and 2 electrons, so 4 kinetic energy terms I have written. The first one is for the kinetic energy term for A nucleus, second is kinetic energy for B nucleus, third is kinetic energy for electron 1, and fourth is kinetic energy for electron 2. So we have these 4 terms for the kinetic energy. Now how many kinds of interaction is possible? Now you see, you have 2 nucleus, so there will be internuclear repulsion. You have 2 electron, so there will be inter-electronic repulsion also. Now each electron will be attracted by both the nucleus A and B. So electron 1 is attracted by electron 1 which is present in A nucleus is attracted by the nucleus of A and the nucleus of B. So 2 kinds of attractive interactions by each electron. Electron 2 which is present in B nucleus is B atom is attracted by the nucleus of B and the nucleus of A. Okay. So 4 attractive terms you have and 2 repulsive terms you have for the potential energy. Now let's see. This is negative sign, so attractive term 1 by 4 pi epsilon naught E square by R1 means R1 is this one. Then minus 4 pi epsilon naught E square by R2, R2 is this one. Okay. Then you can write minus 1 by 4 pi epsilon naught E square by RA. Now it is the first electron, second electron attracted by first nucleus E square by RA. Then minus 1 by 4 pi epsilon naught E square by RB. So RB is this distance. So the first electron attracted by the second nucleus. So these are the 1, 2, 3 and 4. These 4 terms are attractive terms. Now the fifth term is in the potential energy is 1 by plus term, so repulsive term, and 1 by 4 pi epsilon naught E square by R12. Okay. Plus 1 by 4 pi epsilon naught E square by R. So E square by R is the distance between the 2 nucleus. So altogether H2 molecules have this many terms in this Hamiltonian. Now this is a very, this makes the situation very difficult for getting the wave function for the H2 molecule. Another approximation which simplifies this Hamiltonian is called Born-Oppenheimer's approximation. I think I talked about this earlier also. What we say is that in Born-Oppenheimer's approximation, the nucleus being very heavy are supposed to be static, frozen, and only electron movement we take into account. So the moment you do this approximation, all the kinetic energy term for the nucleus goes and you get rid of these. Okay. So if kinetic energy terms for the nucleus goes, then at least two terms on the previous slide goes. One of first one and second one, because these are for the nucleus. So two terms goes, and now you have this one. Here also it's written H2 molecule. Okay. So this is the same equation which was on the previous slide. So this term will go and this term will go. Okay. You will not have after the Born-Oppenheimer's approximation. So this term goes and this term goes, but rest of the term remains. Okay. What we can do is that we can combine this with the E1 with this one, and we can write it together. These two I have written together. Then I can write these two together. So these two together, and rest of the term, and I have removed all 1 by 4 pi epsilon naught for simplifying this equation. So now it is E square by RA. So this I have written already. E square by RA minus E square by RB plus E square by R12 and plus E square by R. So now at least the Hamiltonian looks slightly simple as compared to the previous one after Born-Oppenheimer's approximation. Okay. Once you have this Hamiltonian, here also you have, if you look at this term, why I have combined these two. If you go back and see this one, if you apply Born-Oppenheimer's approximation to hydrogen atom, this will go. Okay, and what you will have, minus h cross square divided by 2m del E square minus E square by R. Okay. So after Born-Oppenheimer's approximation, whatever you have is written here. This is what you get. Minus h cross square divided by 2m del E1 square minus E square by R1. This is what you get. Okay. And remember, there is some, don't get confused, because this R1, make this R1, make this R2, because I will always make this E1, make this E2. Psi A, with A atom you have E1 electron, with B atom you have E2 electron. So that will facilitate, the relationship will not change, but just image you can correct. Okay. So you have a hydrogen atom Hamiltonian here, you have another second hydrogen atom Hamiltonian here. Okay. And then you have these terms minus E square by RA minus E square by RB plus E square by R12 plus E square by R. Okay. So two repulsive terms is still there. Now what happens is that out of these terms, this is something which is not constant. R12 is the distance between the two nucleus, and with the knowledge of the previous module, you know that we are talking about electron density. Okay, which changes with the which may change from one time to other time. Okay, and so this is not a constant term, not a constant. Okay, so this also complicates the thing. Now what we have done is, for this Hamiltonian, what I have done, I have assigned E1 electron to atom A and E2 electron to atom B. Okay. So if you have to write the Hamiltonian, the wave function for this, what you can write? You psi A, you can write a wave function for this hydrogen atom, and psi B you can write a wave function for this hydrogen atom, and one of the electron which is attached to A is E1, so you can write psi A1 and psi B2. Okay, in H2 molecule you have this situation. Now what happens that if the two hydrogen atoms are very far apart, or distance between the two is infinity. Infinity doesn't mean literal meaning of infinity, doesn't mean infinity. It means that at a distance where the interaction is not taking place, A and B, then you have individual electron attached to a nucleus. First electron at E1 attached to this molecule, and E2 attached to this atom. Okay. And what you write the wave function? The wave function which you write is psi A1. Okay. For any atom you can write this one. Psi indicates the wave function. A is for the individual atom A, hydrogen atom A. Both A and B are hydrogen atom, but just to make differentiation we are writing A and B, so that we know there are two hydrogen atoms. Okay. But both are same hydrogen atom. We are talking about H2 molecule. So when they are far apart, when they are not interacting, each of these system, the hydrogen atom A and hydrogen atom B could be represented by wave function psi A1 and psi B2. When they approach and come close together and they start interacting, then I said you that whenever you have a system where more than one wave function is present, the total wave function is the product of the component wave function. So here also you have two different wave functions. So total wave functions, if you have to write, then the only way out is that you write one of the wave functions psi 1 as psi A1, psi B2. But the moment it is bounded, now differentiating and saying that first electron E1 remains with A and second electron E2 remains with electron B is not feasible in a molecule that you know. Okay, from whatever chemistry you have learned till now, that you know that it is not feasible to say that the identity of the electron will be attached to the identity of the nucleus in a H2 molecule. Okay, so now since the identity is lost, any electron can be with any of the nucleus. So it is just possible that electron 1 may go and interact with the electron B in the vicinity of B, and electron 2 may go in the vicinity of A. So an exchange of electron is also possible with respect to the nucleus. So this system, which is a bonded system H2 molecule, can be equally represented by another wave function psi 2. Equally represented by a psi 2, which is say that now the electron 2 is this number 1 and 2 is for electrons, and A and B is for nucleus. Okay. So both these wave functions are equally feasible, psi 1 and psi 2 for a bonded H2 molecule. And if it is equally feasible, then what you say that, and if I say that for the time being, I don't say equally feasible, I say both are feasible. We don't know whether it's equally or unequally for the time being. But then what we can write, the total wave function we can write as linear combination of atomic orbital. So the total wave function psi we can write as C1 psi 1 plus C2 psi 2. And this wave function is the valence bond wave functions given by Hitler and London. Hitler-London wave functions. Okay. If what you can do, you can expand this also, but anyway for the time being don't expand. Okay. Now if you have this wave function psi VBT, you can write psi VBT, then you can apply the Schrodinger wave equation. Schrodinger wave equation is what? H psi is equal to E psi. So Hamiltonian is there. I have not tried written the Hamiltonian. Hamiltonian is there. Now you have C1 psi 1 plus C2 psi 2 is equal to E C1 psi 1 plus C2 psi 2. Now what I do is that I multiply by C1 and integrate over the whole space. So if I multiply by C1, this term, what will be the first term? The first term will be C1 integral of psi 1 h psi 1 d tau. Okay. The second term will be, I mean multiplying by psi 1, so psi 1 C2 psi 1 h psi 2 d tau. Any constant you can multiply. So psi 1 h psi 2 d tau. Then on this side, right hand side, you have C1 and E. So C1 and E you can bring outside because E is a constant, C1 is a coefficient, so it will be constant. Energy is an eigenvalue, so it's a constant. So what you can write psi 1 d tau. then C2 into E, psi1, psi2 d2 you can say, right? Okay. And this you remember, I talked about in the H2 plus molecule ion. Okay. Psi1 H psi1 d2 is called Coulomb integral. Psi1 H2 psi2 d2 is called exchange integral. Psi1 psi1 d2 and psi1 psi2 d2 is called overlap integral. So if you write this one, then it will be C1 H11 plus C2 H12 plus C1 E S11 plus C2 E S12 we can write. And if you rearrange this, then C1 H11 and C1 E S11 you bring this side. So all C1 term you bring on left side, all C2 terms you bring on the right side, okay, and then you can write C1 into H11 minus ES11 plus C2 into H12 minus ES12 is equal to 0. Okay, this term we got. What we can do is we can get a similar equation multiplying by psi2 and integrating over whole space, and that equation will be C1 H21 minus ES21 and C2 H22 minus ES22 is equal to 0. And with these two simultaneous equation, the second one and the first one here, okay, first equation and second equation, and two unknown are C1 and C2. Two simultaneous equation with two unknowns. We have two. This we have done earlier also. So it is a, by now you should not have any problem. Two simultaneous equation with two unknowns we have. So what does it mean? We can write it in the determinant form, and the determinant form is H11 minus ES11, H12 minus ES12, H21 minus ES21, H22 minus ES22, and C1 C2 is equal to 0. Okay. So any one of this is 0. Obviously this determinant is not going to be 0, so this will be 0, and this determinant we have talked about in the MOT, H2 plus molecule ion. Okay. Now out of this determinant, S11 and S22 will be equal to 1, because that's a normalization condition. And if you use this one, then what you can write, this determinant changes to H11 minus E, H12 minus ES12, H21 minus ES21, H22 minus E is equal to 0. I didn't write S12 as 0 because this is not the orthogonality condition. What you have been taught is that if you have psi1 d tau, it is S11 and this is normalization condition. If it is psi2 d tau, then it is S22 and it is 1. Okay. But if I say psi1 psi2 d tau, I have written S12. I do not put it is equal to 0. Normally, what you do? You say it to be 0 because of the orthogonality condition. Let's see why I have not written psi S12 is equal to 0. So if you look at the psi S12, what is this? It is psi1 psi2 d tau. And what is your psi1? Psi1 is psi A1 psi B2 and psi A2 psi B1 d tau. So it is your psi1. Remember this one? This I said you that the two electrons could be exchanged between the nuclei. So your electron 1 was with nucleus A here in the first term, and then electron 2 is with the nucleus B, second nucleus. Okay. So first electron with A, second electron with B. If you look at psi2, second electron with A and first electron with B. So if you find this one, what you can write is psi A1 psi B1 d tau and psi A2 psi B2 d tau. Okay, this you can split into these two equations. Now what happens if you look at this integral, first integral, then your electron 1 is with nucleus A and electron 1 is again with nucleus B also. So these psi A1 and psi B1 are not the of the same system. They belong to two different systems. Okay, and so if the wave functions are different but they belong to two different systems, then psi1 psi2 d tau will not be equal to 0, and it will not fulfill the orthogonality condition, because here yes it says psi a1 psi b1, so they belong to two different systems. Here also you have psi a2 psi b2 d tau, so they belong to two different systems, and so it will not be equal to 0, and it will not fulfill the orthogonality condition. Rather, this will be represented as S, and so S12 will be actually overlap integral will become equal to SS square, we will write. So instead of S12, I can write in this determinant H11 minus E, H12 minus ES square, H21 minus ES, H22 minus E is equal to 0. Okay. So this is a slightly different determinant from what we did in H2 plus molecule ion, okay, or what you will be doing. Now you see from this determinant what you can say that both H12 and H21 will be interchangeable, that and H11 and H22 will be interchangeable because both are hydrogen atom. So the first hydrogen atom and the second hydrogen atom, A and B, is just a distinguishing designation, otherwise both are hydrogen atom, so we can take it as the same one. Okay. Now if you use this one, then what do you get? What you get is H11 minus E, H12 minus ES square, we can write as H11 minus E square minus H12 minus ES square, so it will come on this side, and so H11 minus E you can write as plus minus this one, and then you can write a plus sign, and this will be one energy level, E minus will be another energy level. We don't know whether the energy is high or low or something like that. But we got two energy levels. We did not go for, I just started talking about the exchange of electron when atoms get bonded. And so we devised a valence bond wave function, that's Hitler-London wave functions, and from this we applied the Schrodinger wave equation H psi is equal to E psi. And we got a determinant, and the determinant if we solve, we got two energy levels value, E plus and E minus. Okay. So in order to find out the value of this E plus and E minus, what you need to know is, you need to have the value of H11 known, you need to have a value of H12 known, you need to have a value of S known. Okay. And all these are integrals. So all these integrals can be calculated. One way of doing this integral over S integral is that if you use elliptical coordinates and you use this one, the value which you get is 1 plus r square divided by 3 exponential minus r. So this S is a function of internuclear separation r. Okay. And what does it mean? It exponentially decreases. So if you plot S versus r, you get a decreasing plot. You get an exponentially decreasing plot. Okay. We will, in the next module, we will try to find out H11 and H12 values and see which energy level is higher, which energy is lower. Okay. Thank you.